we'll take our look at the calendar. Today is February 17. We're covering lesson number 8, which is lines of best fit. Just looking ahead in the coming days, on Friday we cover lesson 9, which is in context linear problems. That's going to be some word problems. Then next week, on Monday, we have a catch-up day. It's our only catch-up day of the whole semester, but it's just a day where we're not going to do anything new. We're just going to review and work on stuff that's difficult for us, just a chance to catch our breath. Immediately following that catch-up day, on Wednesday next week, is our second quest. The quest is on lessons 6 through 9. That is to say, it's not cumulative from the whole semester. It's only on the stuff since the first quest. Okay? Questions on the calendar? All right. Then we are starting on page 60. And we'll jump up to the daily summary. In this lesson, we examine plots of real-life data and explore how to use the line of best fit. Number 1 is one of our rare calculator active problems. You'll see a bunch of calculator active problems in this activity today. In 1982, drunk drivers were responsible for 25,165 deaths in car accidents. That was 57.3% of all fatalities due to car accidents. You understand that 57%? There are lots of folks that died in car accidents in that year. Of all the folks that died, 57% of those deaths were as a result of drunk driving. The other 43% had other causes, and alcohol was not involved. So the table below shows percentages of fatalities due to drunk driving for several years. So 1982, 57%, that's the one piece of info that was in the paragraph. In 1985, it was 51%. 1988, it was 50%. Right? We've got this whole big table of data. To display the data in the table, we use a scatter plot. We're going to let P represent the percentage of driving fatalities that were alcohol related at T years since 1980. That is to say that T equals 0 represents 1980. T equals 2 represents 1982, and so on. And so that thing right there is called a scatter plot. Percent fatalities is on the vertical axis. Years since 1980 is on the horizontal axis. Let's go ahead and fill in the coordinates of some of these points. Point A, what are the coordinates? 8 and 50. Just reading it off. The other one is a little bit tougher to read off. Point B, what would you say for the input, the independent variable? Yeah, like maybe it's 19, maybe it's 18 and a half. It's kind of hard to know. I'm going to put 19 here. And then for the Y value, Emma, you said 37 or 38. Well, I don't want to guess. In fact, I don't have to guess. The scatter plot, that diagram, is just representing the table. So the answer to this question is just one of the points in the table. So if we believe that the input here is 19, remember, 1980 is our starting value, so what does 19 represent as a year? 1999, yes, that's this data point. So we just have to go to the table and read off. And what was happening in 1999? What was the percentage? It's 37, and so that's how we know. So I'm going to highlight that row and that point. They both represent the same thing, and in fact, every point in the picture represents one of the rows in the table. Okay, it's just a different way to represent the table. Okay, coming down here, part B, does the scatter plot show any relationship, pattern, or trend between the two variables? That is, does the data appear to be increasing or decreasing or neither? So looking at the data, as time passes, what happens to the percent? Decreases. And it's really easy to see that by looking at the picture, right? Now, I suppose you could have seen that by looking at the data table. 57, 51, 50, 47, 40, 38, 37. So I can see the decreasing nature in both. But the picture, I feel like, gives me more. It wasn't decreasing at a constant rate, right? Like these points are not all exactly on a single line. It was decreasing at different rates, but definitely decreasing, and there's a trend here. And that's what we're after today, is talking about that trend more specifically. So we've answered that question. Appears the data is decreasing. And now part C. On the scatter plot, you're going to sketch a line that you think fits the data the best. And I want you to use a straight edge here. So grab the yellow folder or grab your binder or grab the bookmark. But just draw a line that you think is as close as possible to all the points. I don't want you to connect 2 points. I certainly don't want you to connect the first and last point. I want you to draw a line that kind of goes right through the heart of all of these points. And there are about 15 of us in this room, and we're going to draw 15 different lines here. So there's a lot of acceptable answers to this problem. So there's my line of best fit. It's different from yours. Nobody drew that line. But I just want to point out, I did not connect the dots, right? And I don't want you to connect the dots either. I want you to look at all the points. If you just decide to connect 2 points, you're only using 2 points. You're ignoring all of the other ones. Don't do that. I want you to look at all of them, draw what you think is as close as possible to all the points. Okay, number 4. Since the data in the scatter plot appear to be roughly linear, we can sketch a line that comes close to the data points. We say that T and P, that's the time and the percent, are approximately linearly related or linearly associated. Approximate, it's not perfect. Part A down below, of all the lines that we could draw near the points, the best line, which is the one that's graphed in this picture, has a name. We call the line graphed above the line of best fit for the data, or the least squares regression line, or more simply the regression line. So that right there is called the regression line. So important note, finding the actual line of best fit, which is the one that's drawn here by a computer and not the one that I drew and not the one that any of you drew on the previous page. Finding the actual line of best fit is something that calculators and computers can do, and you can too if you take a statistics course. When we draw a line of best fit, keep in mind that we are just trying to draw a line that is close to all of the points. We are only going to be approximating the actual line of best fit. So don't go crazy, feel like you have to get it perfect. You don't have to, and that's a good thing because it's not possible to get it perfect just by freehand drawing a line, right? Just draw what you think is the best line. So part B, we can use this line to make predictions about the data. Let's use the line of best fit, the one on this page, to predict the percent of fatalities due to drunk driving in 1993. So remember, 1980 was t equals 0. So 1993, what value of t is that? 13. So your job is to go look at this table, look at the graph, and figure out what's going on at t equals 13. So we go to t equals 13, it's there. I go up to the line that's drawn here. You get that? And then we estimate the y value or the p value in this case. What do you think? $42. If you said 43, it's okay. If you said 50, that's not okay. Again, there's different correct acceptable answers here. We're just making our best guess. We'll say 42 or 43 here. So 42 or 43, something like that. So now we're going to come up with a way to do things more accurately than just looking at the picture and guessing 42 or 43. What we're going to do is find the equation of the line that's drawn on this page. How do you find the equation of a line? Well, you need 2 points. So we're going to find 2 points that are on the line. So let's look up at the line and see if we can find 2 points that are on the line. First of all, are any of the points that are plotted on the line? Are any of those points that are plotted on the line? The answer is no. We didn't draw the line by connecting points, right? We drew the line looking to get as close as possible to all the points. None of these points are on the line. The only one well, there are a couple that are kind of touching, but even if you look at this guy, the line doesn't go through the middle of this point, right? The fact that that point is quite thick is the only reason that it appears it's on the line. If I made the point really small, it would clearly be off of the line, right? So the goal here is not to pick points that are plotted, which means you're not going to points in the table. We're going to try to find points that are actually on the line. So, for example, how about this point right here? 16, 40. Is 1640 on the line? You need real good eyes to look at your paper to decide that the answer is no. 1640 is slightly above the line. If you look very carefully, it's close enough. Again, everything we do today is going to be approximations. We're just looking for nice points that we can grab that are pretty close to being on the line. So we're going to grab that one there. Looking up and down this line, I don't see any other points that are like really close to being on the background grid. I think the other point that I'm going to ask us to pick is this guy right here. Guesses for the coordinates of that point? 20,35. Close. I mean, it's not going to be perfect. Nothing we do here is going to be perfect, but those are the 2 points that we're going to use. If you use 2 different points, probably get a different equation, but that's okay. There's a lot of right answers today. So I've got our 2 points, 1640 and 20,35. Notice that I've gone out of my way to write down the letters T and P. This is not X and Y in this problem, and a little part of what we're after today is to get comfortable leaving traditional X and Y land and going to whatever letters are given in the problem. So finding the equation of a line that hits 2 points is a problem that we've done in the last 2 classes. So this is now a familiar problem. We can ignore all the stuff about drunk driving from this point forward. So the first thing we need to calculate is the slope. I've got the beginning of the slope written out here. We know the slope is the change in y over change in x, but I want us to not use x and y here. Instead of y, what do we have? We have p. Instead of x, p, right? P is the new y, and t is the new x. Okay, so now we're subtracting the p values. Is that 16 and 20 or 40 and 35? Okay, so we'll do 40 minus 35. And then downstairs, 20 minus 16. We can't do that way? Jeff says 16 minus 20. Yeah, you can't mix and match. As soon as you make a commitment up on top to do one direction, you got to make the same commitment downstairs. So the way that I've written it here on top, we have to do 16 minus 20 on the bottom. Joel had another viable option, which was to leave the bottom and change the order on the top. Either way, you'll end up with the same answer. Let's write it here. Upstairs is a 5, downstairs is a -4. Oftentimes with these word problems, we'll want decimals instead of fractions. This is -1.25. So there's the slope. But part of this problem asks us to include units, so let's do that now. To include units, I need to go back to the beginning. 40 and 35, what were the units for those 2 numbers? These were percentages, right? So upstairs, the units are definitely percent. Downstairs, I had a 16 and a 20. What were those measured in? Years, right? And so when we say -1.25, we really mean -1.25% per year. So those are my units right there. And it says, interpret the meaning of the slope in this context. Write a sentence in plain English. So let's write a sentence in plain English. I didn't really give room for this sentence. We'll squeeze it in here. Okay, -1.25% per year. Something was changing by -1.25% per year. The percentage of deaths due to drunk driving was changing by -1.25% per year. I'm going to slightly amend that sentence. What does the negative mean? Decreasing. So I'm going to use the word decreasing instead of changing. So we'll just say something like that percent was decreasing by how much? Yeah, 1.25% per year. Notice we didn't put -1.25. Took care of the negative with the word decreasing. Questions on the sentence? Okay, so let's now finish this one by finding the equation of the line. We've got our slope. We can use either of these points. I think most of the folks in the room prefer the y equals mx plus b version. But if you want to use the y minus y1 version, that's okay too. But again, I want us to change the letters here. We don't have x and y in this problem. Instead of y, p, m instead of x, p. So that's our new mx plus b equation for this problem. Okay, first thing we do is we change the m to the negative 1.25. That was the slope we just found. Then we're going to grab the coordinates of either point and throw them in there for t and p. Let's just all use the first point, although it makes no difference which of the 2 points you use. So in the first point, it was 1640, right? How much was the p? 40 equals negative 1.25 times, how much was the t? 16 plus the b, which we are about to find. Just call it b. Okay, 40 equals, what do we get here? 16 is at negative 20? I think that's right. Anybody with a calculator, double check that, thank you. Plus b, so how much is b? B is 60. Since we have the picture of this line in front of us, this is an opportunity to just make sure we didn't do anything silly. Does b equal 60 jive with the drawing, with the line that you have drawn at the top of this page? Remember, b is the y-intercept. Is it close? Okay, it's not perfect. If you were just to estimate the y-intercept of the line that's drawn, what would you say? 58? 59? How come it's not perfect? The line is perfect. The line is the only thing that's perfect, because I asked the computer to take care of it, and the computer knows the formula to get it perfect. But when we said 1640, was that perfect? No. When we said, what was the other one? 2035, I think. Was that perfect? No. Those two imperfections are going to lead to imperfections in our equation. So the line is right. We are wrong, but it's close. And that's all we're after today, just close. So finally, the equation of our line, copying this guy, but changing the b to 60. So we get p equals negative 1.25 t plus 60. Questions on the process, finding the equation of that line? Okay, when we're ready, we're going to the next page. We're just going to rewrite that regression equation right here. P equals negative 1.25 t plus 60. Step 4. In this case, we can figure out how accurate we were when we picked nice points on the line. The equation of the actual line graphed above, according to GeoGebra, which is the piece of software that I used to make that graph. The equation was y equals negative 1.19x plus 58.63. How far off were our slope and y-intercept from the actual line? Okay, let's compare for a second. So the slope of the real line is negative 1.19. What's the slope of our line? Negative 1.25. Seems quite close to me. We're off by 6/100. It's not too much. And then the y-intercept of the actual line was 58.63. Jeff was very close when he said 58.59. It was almost halfway between his two guesses. Our answer was 60. That's close enough. It's not going to be perfect today. Okay, part E says use the regression line to predict the percent of fatalities due to drunk driving in 1993. It's actually a problem we've done already today, but we're going to do it in a different way right now. Again, we got to figure out what value of t corresponds to 1993. And one last time, 0 was 1980. So what value of t is this? 13, right? And so we're going to take that t equals 13 and we're going to shove it into this equation. This equation will output the percentage if we plug in a t value. So let's do that. P equals negative 1.25 times, instead of t, 13 plus the 60. Somebody with a calculator help us out here. Lauren? Can you add the 60? What is it? I think we lost the negative in there. $43.75. Okay. That is our best guess for what was going on in 1993. What was our guess when we looked at the line on the previous page? We made a guess. It was 42 or 43. So the real answer, according to our equation, is 43.75. Now that's not the right equation, so it's not as good as it could be. We probably, if we had the software, should have plugged the 13 into this equation. That's the best equation, and then we'd have our best guess, right? But all we're doing is drawing a line of best fit, picking 2 points, lots of estimation. So again, there's a wide range of correct answers. Okay, since we were using our regression line to estimate or predict between known data points, this problem was about 1993. Going all the way back to the chart, what was the earliest year? 82, and the last year? 99, and the question here about 93 is someplace in between, right? 93 is not in the chart per se, but it's between the extremes of the chart. So if you use your regression line to predict something between the start and end of your chart, then it is called interpolation. Inter means between, that prefix. But now we're going to use a regression line to predict the percentage in 2002. And 2002 is outside of the table, right? It's past the end of the table. So let's go ahead and use our regression line here. What value of t is this? 22, right? 1980 is 0. And so we're going to do the same equation from the top of this page. P is negative 1.25 times 22 plus the 60. And this is 32.5. So that's our best guess for what was going on in 2002. But in this case, because 2002 is outside of our table, it's beyond our table, this has a different name. It's not called interpolation, which is between, but it's called extrapolation. That EXTRA prefix typically means something outside. Generally speaking, it is much safer to interpolate between than to extrapolate, which is outside of the realm of the table. And the danger with going past the bounds of the table is that something dramatic might have changed outside of the bounds of the table, and that change would not be reflected in the table. And so, for example, in the year 2000, which is after this table, maybe all of a sudden police cracked down on drunk driving, and so there was an impact. And that impact wouldn't just necessarily follow this kind of nice linear trend that we are making our prediction based on, okay? So you do the best you can with the equation that you have, but just know that there is a danger in going beyond the bounds of the table. Okay, so the activity starts on the next page. Again, these problems are all calculator active. And again, as you check your answers with each other and as you check your answers with my answer key, know that you are probably not going to agree with each other exactly, and you are probably not going to agree with my key exactly. Just need to be close.